Good morning again. Today's class, we're gonna finish chapter 6. We're gonna cover the last application of using the timers to measure timing between events. And we're gonna talk about the Watchdog Timer and the sleep mode of the microcontroller. Oops. And I assume you see my screen. Okay, so we covered hardware delays, we covered periodic interrupts, and we did an example with a fully empty main loop, and everything was done in the interrupt service routine. We saw how to use an external clock for the timer 0, and we use it to count events. And the last application I'm going to talk about is how to measure timing between events. Okay, just like, okay, something like this. If you are required to measure a time between two rising edges, or between two rising edges, this time t, or a time between a rising edge and a falling edge for a pulse width. So how can we do that? And I'm not going to write a code, okay, to move faster, but we can write it on the board or do quick examples on the board. So if you are required to measure that you have a signal coming from, I don't know where, from any system, okay, and you are required to measure this time, which we call what? The period, right? Right? Between two rising edges, or measure this time between a rising edge and a falling edge, t, duty, or is this duty in period? Whatever, t1 or t2. How would you do that? You can think of timer 0, right? We know how to make timer 0 count in a speed that we set, right? We can make it count as fast as the oscillator clock over 4. In our case, the oscillator clock was 8 megahertz over 4, 2 megahertz, right? So we can make 1 over that, right? 1 over that. So we can count from 1 over 2 megahertz, count every 0.5 microseconds, right? And we can prescale that up to 256, which is 128 microseconds, right? So we can choose how fast we count. You can use the interrupts to latch or copy the value of the timer when a rising edge happens, and copy it when a falling edge happens, and keep the timer 0 overflow interrupt tracking how many overflows happen before the next edge comes. Let me give you an example. Assume you want to measure this pulse width. And I told you that the rising, we enable timer 0. So I'm going to write pseudocode. Enable timer 0, interrupt, and make it مثلا count every 0.5 microseconds. يعني على oscillator clock زي هيك. على 8 megahertz oscillator clock, i.e. 8 megahertz oscillator clock frequency with no prescaler. Okay, so you enable timer 0 in the endcon register, right? So global enable and local enable for timer 0 overflow. You set in the option register this timing. you choose not to use the prescaler. You select the option, the oscillator clock divided by 4. And then you can do an external interrupt and enable the external interrupt to happen on a rising edge. Enable external interrupt on rising edge. So, and tie this signal to port B0/INT, right? External interrupt pin. So whenever a rising edge arrives to this external interrupt pin, an interrupt will happen. You will go to the interrupt service routine. Inside the interrupt service routine, right? You check if it was the external interrupt. You can do what? You can say timer 0. Take it and save it at some memory location. You do like an integer مثلا, called edge 1. تمام? And you set the next interrupt to happen on a falling edge. So next time you'll come here لما يصير falling edge يعني هون. Okay? بعدين so you have the value edge 1, which is the value of timer 0 when this happened. And let's say مثلا هاي value كانت 0x34 مثلا. Then timer 0 continued 35, 36, 37 بعدين FF بعدين it overflowed here. Overflow after FF it went back to 0, 0. But then it counted from 0, 0 to FF and overflowed here and overflowed here. But then it counted until مثلا هون 0x04 مثلا. Okay? But then a falling edge happened. And so an external interrupt is going to happen. So you can do some logic here. If this is the first time, يعني ممكن تعمل انت اول ما تدخل هون تعمل I++ تكون I اصلا 0. If I equals 1, you do this, صح? If I equals 2, this is your falling edge, صح? So take the value of timer 0 and save it at edge 2. خلاص disable external interrupt disable the overflow interrupt. Okay, خلصنا. هلا if the overflow interrupt, if timer 0 overflow happens, here just have an overflow counter increment every time you overflow to count how many times you overflowed here. So in our example, يعني I wrote the code, now you're at a level you can just go and code it in micro C. So I know that an event happened at value 34, a rising edge, a falling edge happened at value 04, and I have three overflows in the middle. So what is the time between these two events, the rising edge and falling edge, which is the pulse width? First of all, we tried to find out how many counts we counted, but then we know that every count takes 0.5 microseconds, right? So you can know the time. The counter is an 8-bit counter, right? 8-bit timer or counter, whatever. So to count from 0, 0 to FF and overflow, this takes 2 to the 8, right? Yani 256. 256 counts من الأوفرفلو للأوفرفلو ومن الأوفرفلو الثاني للأوفرفلو الثالث 256 counts, right? And from this overflow to the falling edge, it is 4, right? 4. طيب, from 34 hex to the overflow is how much? لFF بعدين overflow. So it is 256 minus 0x34, right? Right? Then our number of counts, right? Number of counts equals 256 هاي decimal decimal وإذا بدك إياها بالhex it is gonna be what 0x100, right? اللي هي 256 اللي هي what كمان 2 to the power 8 plus sorry minus 0x34 plus 256 اللي هي هاي كمان ايش 2 to the 8 يعني 2 to the power 8 plus 256 plus 0x04 قديش الكاونتس؟ احسبهم. Yeah, you can count them. Let's say counts خلاص counts. Just go use a calculator. Counts. طيب, the time between the events is counts times the time per count, which is 0.5 microsecond. Okay? Easy, huh?
Yes.
طيب. So it's how you apply. And all what we used an external interrupt, we used the timer overflow interrupt, and we did this application. And you'll have an exam question on this, okay? Now, the way we did it, we did count how many overflows in the middle. We computed the okay, time after the last overflow. We computed the difference between the first overflow and the rising edge, right? If you want it systematic, this is an equation. So if edge 2 is larger than generic edge 2 is larger than edge 1, then the pulse width will be the number of counts times 220 to the power 8, which is 256, plus the difference between edge 1 and edge 2, edge 1 and edge 2, okay? If edge 2 was less than edge 1, the pulse width is the counts minus 1 times 256 plus 256 minus the difference, okay? And you can do it numerical and verify these. So this was the last application I was going to talk about, timer 0 overflow and how you can make use of it. We come to the watchdog timer. Watchdog timer is a very important concept. Watchdogs, there are many, a watchdog in embedded software is a piece of software that keeps watching something or guarding something, so nothing bad happens, okay? For example, a watchdog timer is a piece of software that would cause an interrupt. We talked about it early in the semester, but let me remind you, it's like a dog sitting there guarding or watching a farm. And that farmer goes out every 2 hours and feeds the dog, okay? If something bad happens to the farmer and he doesn't go out and he doesn't feed the dog will start barking, right? And make noise and let everybody know that we have a problem and those will come help. Same here. A watchdog timer is a timer similar to timer 0 that we could have full control of how fast it increments. It's a counter, 8-bit. You, as the owner of this code, the embedded software, you go and reset the timer every amount of time. So let's assume it overflows every let's say every 20 milliseconds, for example. It overflows. So if it overflows, it will cause a reset. So your job is not to allow it to make a reset. So you go out and you every 10 milliseconds, you reset the watchdog timer. Okay? If you reset it, it will not ever reach its maximum, the FF. So go back to 0. Count 0, 0, 0, 1, 2, 2, up to FF. And then you manually go reset it. So it's never gonna get to FF and overflow and cause a reset. But if you are in if there is a bug in your program, you got stuck in an infinite loop, so your code, the line that will write a 0 in the watchdog time register, is not gonna execute. So the watchdog timer is gonna continue running in the background, incrementing, until it will reach its maximum and overflow. And this will cause a reset, which means taking the program counter out of that infinite loop and sending it back to address 0. Okay? So this is the main job of the watchdog timer. Okay? A watchdog timer will always reset if it's enabled. And how do we enable it? If you remember, there was a configuration word when we first programmed our microcontroller. You enable or disable the watchdog timer. If you enable the watchdog timer, it will count all the time in the background. It has its own clock. Okay, it has its own clock, and it overflows every 18 milliseconds. If you go search the book, I have the number here. I think I have it. The clock speed is set to make it overflow every 18 milliseconds. Here, okay? Without a prescaler. And you saw that in the option register, we are able to assign the prescaler we use to timer 0 to assign it to the watchdog timer, which is slowing this down. And if you make a 1 to 2 prescaler, this means instead of overflowing every 18 milliseconds, it will overflow every 36 milliseconds, and so on. So you can slow it down using the prescaler. Okay, so if a watchdog timer, if you enable it, it will start. It will start counting. How do you clear it? There is an instruction in assembly called clear watchdog timer. Okay, if it reaches its max, it will overflow, reset the CPU. And you should know how fast it counts, because you know what is the prescaler and you know the clock speed. So you should go in your code, you know how fast your program code is, how fast is your oscillator clock, how fast are instructions executing. So you can decide, okay, every 2 lines of code, I'm gonna write a reset or a clear watchdog timer. Okay. So this is the main thing that the watchdog timer does. It resets the CPU whenever it overflows, if you are running normally. However, if the CPU is in the sleep mode, so the watchdog timer does a reset. Okay. After the reset, well, you go back to program to address 0 and you continue running. If you have enabled the watchdog timer and you want to know that something wrong happened, you should check the values of the 2 bits in the status register, the timeout, and there was another bit in watchdog timer in the what was it? The status register. Okay, and you can get an indication if a watchdog timer has caused a reset, or is it a normal startup after power on. Right. Another use of watchdog timer is to wake you up from a sleep mode. There is an instruction in assembly called sleep. The sleep, what does sleep do? Okay, we'll talk about what does sleep do. But if a watchdog timer And if you go to sleep, the watchdog timer will continue counting in the background, even if you are sleeping, even if the CPU is sleeping. If the watchdog timer overflows while you are in the sleep mode, it will cause a wake up. Yani, what does a wake up mean? I'll talk about that. First, let's learn what does a sleep mean. A sleep means that the microcontroller almost goes into suspended animation, which means the clock oscillator is switched off. We know our microcontroller, we have a clock, right? Oscillator clock. And the instructions execute in a speed, in a frequency that equals the F oscillator divided by 4, right? Which is the instruction cycle. If you disconnect the clock, then the program counter is not going to increment anymore. It's not going to fetch instructions anymore. Nothing is going to be executed. Suspended. Everything stops. No instructions are going to be executed. Okay? But if you have a port, let's say port B0, that has a 1 on it and an LED on, it will stay on because we have a flip-flop here that retains the one that you wrote. And switching the clock means that we're not going to take new input, but the input in the flip-flop is going to stay there, right? Basics. So, and minimum power is going to stay there for the RAM to retain the data in it, okay? So disconnecting the clock will stop new instructions from execution, but values in data memory will stay there. Values on ports will stay there. This is going to sleep mode. This is the meaning of going to sleep mode. Disconnecting the oscillator clock, okay? If a watchdog timer, when you say sleep, the first thing, the oscillator clock stops. The watchdog timer is cleared. يعني يبلش بصير قيمته صفر. Okay? عشان يبلش يعد من البداية. It will keep counting if we don't use a prescaler. After 18 milliseconds, okay, it will overflow. This will cause a wake up. Wake up means reconnect the oscillator clock and start executing, going back to normal as usual after 18 milliseconds. Okay? Imagine how this is helpful. If you have something, you're controlling the climate in a room, for example, and all what you do is read a temperature sensor, check the set point by the user, what is the temperature he wants, and then decide to turn on or off the compressor. Do you need to do that every microsecond or every 1 millisecond? No, every 1 second will do it. Okay, so you can enable watchdog timer with a prescaler and make it overflow every 1 millisecond, every 1 second, let's say. Okay, and go to sleep. If you go to sleep, usually the typical value of power consumption goes down to 1 microamp. Okay, 1 microamp. So if you are running on a battery, if it's a standalone system, you know, if it's, let's talk about a system measuring the air pressure in the tires of your car. Imagine that sensor, the microcontroller that reads the pressure in the tires of your car is always on. How long is this battery live for? Okay, imagine if you make it sleep and wake up every, I don't know, a few seconds, 1 second, okay? Do something for like 1 millisecond, then in 1,000 milliseconds, you're only doing something 1 millisecond work, then you are saving 999 milliseconds doing nothing and dropping down the power consumption to the minimal. Okay? So the watchdog timer can be used to wake up the microcontroller from the sleep mode. Okay? Program execution is suspended. Yani when you do sleep, you switch the oscillator, watchdog timer resets, program execution stops, all ports and data memory retain their current setting because the power is still there, but at its minimum. Okay. The power down and time out status bits in the status register are cleared and set respectively. Okay, so you can know when you wake up after that you were in a sleep mode and the watchdog timer woke you up. Okay, if enabled in the configuration word, the watchdog timer will continue to run, and if it overflows, it will wake up. It will reconnect the clock and everything will go back to normal. Sleep mode is a very useful tool to power save. Okay, if you are in a sleep mode, what wakes you up? There are three things that can cause the CPU to wake up. If you are in the sleep mode, meaning that the oscillator clock is disconnected, the program counter is not moving, no code is being executed. What can you wake you up and cause the controller to go back to normal operation? Three main things. First, an external reset. A reset on the master clear pin. If you push the reset button, okay, this will cause a reset. It will take the program counter back to address 0 and start executing from 0. Okay, reset everything. A watchdog timer wake up. This is what I was talking about a second ago. If the watchdog timer is enabled, it will continue running. Whenever it overflows, it will cause a reset. It will cause a wake up. And there is a difference between a wake up and a reset. A reset will cause the program counter to go back to address 0, right? While a wake up will continue from the point where it was, because the program counter at the end of the day, it's a register. It has a value. It points somewhere. If you go to sleep, you disconnect the clock, so it's not going to increment, but the value that it used to have is going to stay there. If you bring back the clock, the value is there, so it's going to execute that instruction it's pointing at and continue. Okay? The third cause of a wake up is an occurrence of an interrupt, but not all interrupts. If an interrupt, first, an interrupt has to be enabled. Okay? If any enabled interrupt is enabled, and the interrupt happens, let's say an external interrupt on port B0 happens, it will wake up the microcontroller. E square prime right complete interrupt will cause a wake up. What else? Port B change will cause an interrupt, will cause a wake up. But timer 0 overflow will not cause an interrupt. Why? Can anybody tell me why? Because it's timer 0 runs on the oscillator clock, right? Right? It increments.
Yes,
every 0.5 right microseconds. If this was 8, so if this is disconnected, the timer 0 is going to stop counting. It's going to stop counting, so it's not going to overflow. ماشي.
So لو كان جاي من external clock source.
Okay, good question. Honestly, I never tried that. It was trying. Or I need to search for it. I'm not sure if it's mentioned. If it, for sure, we know that timer 0 overflow will not happen if it's running on the oscillator clock. But if it's running on an external clock, does it cause a wake up? Maybe we need to read more in the data sheet.
دكتور حسب رسمة الهاردوير اللي ورجتنا إياها المرة الماضية الأصل إنه يس.
Yeah, it overcomes the oscillator clock, but we need to make sure that is accurate. No prescaler. Okay, we'll look for it. Okay, prescaler, watchdog timer, wake up. We need to look for it in Okay, I'm not. I'll look for it offline. ماشي. تمام. So this is a sleep mode, and the main purpose of it is to save power. Okay. Last thing, interrupt latency, and we're gonna end. When some interrupt happens, how much time does the CPU take to respond to that interrupt? A rising edge happened. You're executing some code in your main loop. Timer 0 overflow happened, or an external interrupt happened. We say the response is immediate. Well, however, there's some delay. How much is this delay? This delay is equal to the time needed to finish executing the current instruction that is being executed when the interrupt happened. Then the time needed to push the program counter to the stack, and this is done by hardware. And then the time to write 00 to the program counter, make program counter point to the interrupt service routine. And then the time to fetch the first instruction in the interrupt service routine. Okay. So this is for clock cycles. This is in its best case 1 clock cycle, worst case 4 clock cycles if you just started. So if you want to compute the worst case scenario, 4 plus 4, that's 8. And pushing the stack and loading the stack, I think it's one clock cycle because the hardware does it. Okay. So you can, and if you don't know, by the way, you can make an interrupt and write a 1 to a pin, for example, on a port, and connect it to an oscilloscope. Okay. And when an interrupt happens, you go turn it off inside the interrupt service routine and can measure this time. And you can make the reset timer 0, for example, reset it and write a 1 here. Okay, then this will go high. Inside the interrupt service routine, you can make it go low and tie this to a scope and measure it if you want really accurate timing. Okay, summary, interrupts are very important, very helpful, make you think of unconventional way that you're used to writing programs, okay, to utilize time, to utilize the limited resources in the limited resources in or let's say optimize the CPU time. Okay, time is over. I was thinking that we can start chapter 7, but probably not. Chapter 7, I'm going to cover 3 main topics in it. We continue Tuesday, inshallah. Thank you very much.
يعطيك العافية دكتور.
Tuesday. Allah يعافيك.
يعطيك العافية.